Well, thank you. It's good to see you here this evening. I like the informal setup. Like Jesse said, my name is Eric. I work here at Atomic. I'm a software developer. The first question I have for you, I expect this to be interactive, so you'll get to participate or have to participate as the case may be. How many of you have heard of lambda calculus? Okay, a number of you. How many of you have heard of pi calculus? Okay. Well, after tonight, you'll have heard of pi calculus. So what we're going to do is I'm going to talk about communicating sequential processes and give you some background on the problem that it's trying to solve and how it goes about it, what it's like to work with it, and then we'll go into some examples using the Go programming language, which is very directly related, and then give you a feel for some of the syntax. By this point, Go has been out for several years. A lot of other languages have picked up on the ideas that Go is trying to share about how to go about doing concurrent programming. So like Jesse mentioned, Clojure has a core async library which tries to do communicating sequential processes very much like Go does. There are some other libraries for things like Python and Ruby that use the mechanisms that those languages have, whether it's threads or what might be called green threads or coroutines, and we can talk more about that later if you're interested. But to start out with, there's a problem. The original version of this talk was called effective communication, or why telepathy might not be such a good idea. And this is really the telepathy problem is more or less what you have right now in software development when you try to do low-level concurrency programming. You've got a lot of different things going on at once. You've got different processes or threads, and they're all trying to access the same memory, the same variables, and that can create a whole host of problems. It can create new problems when you try to solve it using particular solutions. And in particular, it all comes down to non-determinism. You've got a lot of different processes going on at once. You don't know which one is going to happen when. Sometimes they'll be interleaved. So if you have two different threads just printing a stream of numbers, you can end up with two numbers from one thread, a number from another thread, three numbers from the first thread. You don't know what's going to happen. It's going to depend mostly on the operating system scheduler, not on anything in your code. And that creates race conditions where one thing happens before something else, and you get into a bad situation because suddenly you have two things that are, say, both trying to update a number at the same time or change some values. And in the effort to solve those, you might use mutexes or locks, and that can actually create a situation where you have deadlocks, where you have all these different threads all waiting on each other before they can do anything. And because these problems are non-deterministic, they're very, very difficult to reproduce. And when they're difficult to reproduce, that means they're difficult to debug. And when things are difficult to debug, you have a hard time creating reliable software. So with so much depending on software these days, reliable software is very important. You want your bank to have reliable software. You want your health insurance company and your hospitals to have reliable software. So if you've got a lot of different things going on and you're in a situation where you have non-deterministic code because you've got concurrent code, then sharing memory can lead to buggy software that people feel is unpredictable. So there's a variety of solutions to trying to handle the problem of sharing memory. And these are just a few of them. Some are better than others. But ultimately, they all share some common weaknesses. And one of them is that they're complex. There's a lot of conceptual overhead to deal with anytime you're doing this. Say you want to update a value. If you know that other threads might have access to this value, then you've got to, say, wrap it in a lock. Do you have the lock? If not, what do you do? Do you wait longer? Is it possible that you're in a deadlock situation? When you are done, you have to make sure to unlock it if you're using it. Otherwise, the other things that are waiting on it won't be able to proceed. And it's doable, but it's easy to mess up. This is sort of the concurrent, this sort of parallels memory management, that if you're not confident about how it should be, it's very easy to start creating memory leaks in places. Here, it's the opposite problem. It's not stuff just running off ahead and growing bigger. It's just stopping dead in its tracks because it's waiting for something because you forgot to release a lock that you had created. One of the other weaknesses that it has is that those can be leaky. When you're dealing with, say, a function that deals with locks, you might not think about calling that function having to do anything with other threads. You might think it's perfectly safe, that there's no reason it should share it, but deep down, you end up having to deal with other threads. And then anytime you call that function, you have to start worrying about whether or not, you have to start worrying about what that function is doing down at deeper levels. And the third problem that it can have is that the solutions to these different concurrency problems don't necessarily compose very well. You might end up taking two things that seem to work well, and when you put them together, say atomic operations and transactions or mutexes and locks, that you get unexpected behavior. There's not a reliable way to necessarily think about these things. And you generally don't see sort of like higher order locks or some of those things that show that the concept is composable. So what we want out of a concurrency solution is something that's simple, abstract, and composable. And of course, we want it to be concurrent. And so where might we look for inspiration? Does anybody have any ideas? Erlang, okay. The actor model is one example. Scala also, I think, has the ACA library for doing the actor model. That's a good point, and we'll touch on that a little bit later. Has anybody in here done any sysadmin work? Has anybody done any shell scripting? What's one of the things that you learn in shell scripting beyond just invoking programs? It's one of the core sort of paradigms in, say, the Unix philosophy, but about how you stick programs together. Message passing, pipes. So pipes are a really good place to start thinking about CSP, communicating sequential processes. For starters, they're simple. It becomes very easy to take one program's output and send it as the input to another program. In fact, it only takes one character in a shell scripting language, generally speaking. And it really is not any more complicated than that, and that means that you can chain several of those steps together. I know that I've written shell scripts that use piping, and then you end up really proud of it because of the information that you were able to parse out of maybe a very big log file or some other things that show that it works very well to just glue piped output into piped output. And so they stick together very well like Lego blocks. They're also parallel. They can all run at the same time, right? The first program, when it's done with a line of text, it can hand it off to the next program, and then that program can work on it while the first program is still working on the next line. The classic example in this case is doing your laundry. Once you take the clothes out of the washer and put them into the dryer, you can put a new load into the washer and have them going at the same time. And generally speaking, this is a very non-leaky way to compose your programs together. Rarely does one program have to concern itself with even the implementation language of another program. All it has to worry about is that interface boundary. What does the input look like? And so you can use completely different languages, and you don't have to worry about the internals of what comes before you or what goes after you. And so that's a really good starting point for thinking about communicating sequential processes. This is it's actually an algebra described by Tony Hoare. And if you wonder why he's called Tony, it's because the A stands for Anthony. All the way back in 1978. You may already be familiar with some of Tony Hoare's work. He actually invented, when he was 26, the quicksort algorithm. And we take it for granted today, but that was 1960, so that was non-trivial in those days. And so CSP is really less invented and more described because it's more of a math. It's not, say, necessarily even a language. It's an algebra. So I mentioned it was called pi calculus. And Hoare's paper generalized some principles of what pipes deal with at a very shallow level. And he created a whole notation for describing it. And lest you worry, this is all the math that we're going to have in this presentation. If you'd like to read more, you can read his papers, which have more of the abstract formalism very thoroughly. But what we're going to talk about here is more of the pragmatic side of CSP and actually using it. Yes?
Will you link to some of those?
I will dig those up, yes, and I'll supply links. And so if you're interested in the algebra, which it's dry reading, but it's not too bad, all things considered. He doesn't just jump into trying to make it as abstract as he possibly can. It's really fairly basic, and it's a very gentle introduction. And the reason I bring up the fact that it's an algebra is not because you have to understand that algebra in order to really use CSP. I know sometimes if you're familiar with Haskell, you might feel like you have to understand category theory in order to be able to use Haskell. And CSP is not the case. The reason I bring up the math is because it really demonstrates that it's something that you can easily reason about. They've actually created a whole mathematical notation describing what's going on here, and there's rigor behind it. And so it's not just the sort of thing that's been rigged up and just happens to work, say, like a Turing machine. So you probably, I know I haven't heard of like a mutable object calculus or monkey patching algebra. So those by comparison are much sort of conceptually harder to reason about strategies for dealing with different problems. And this is really something that at the ground level, without any computers involved whatsoever, is solid and something that you can think about.
Do people use the term monkey patching algebra?
No. There's a reason, is because it's not something that you can apply any sort of mathematical rigor to. It's just like, well, I did this and it works. And so that's usually a sign that you're in for trouble down the road. So the whole idea here is to make software more maintainable. And the CSP is really built on two very basic primitives. The first one is processes. This is not necessarily talking about your operating system processes. This is a generic process, which you might think of as an ordered sequence of operations. It is not something that you have threads within a process like you would for an operating system process. And in the math, there's no shared memory. If one process has some object or value, no other process has access to that. So they're not sharing anything. And that starts to solve a lot of your problems that you end up with in trying to create concurrent software.
No shared mutable memory. They could be shared.
We'll get into that a little bit. And if you look in the original paper, the math, nothing's mutable in math. So what the idea is that when one process hands a value off to another process, it no longer has it. If you start thinking in terms of immutable objects, it's much less of a problem, right? You think of it, it handed off a copy of this. It's just this one operation is to copy it and pass it off. And then you don't deal with that. The original formalization of it is really just saying, like, once you hand it off, you no longer can do anything else with it. Which, you're right, in practical terms is not the way that you end up dealing with values. So the other primitive is channels. These are the ways in which processes communicate. And you can pass whatever you want. So pipes, you can pass text. You maybe pass bytes. When it comes to channels within a programming language that implements CSP, you can really pass whatever you want. It can be whole.
Channels pass other channels?
They can. I thought about having an example of that, but I've still not come up with like a really good reason to do that. The closest I've got is some sort of like connection pooling that you can say, pull from this channel, and but you can definitely do that. So anything in a language that's a value, presumably. I'm speaking in terms of Go, since that's most what I'm familiar with it, as far as its CSP, is anything that's a value in the language you can pass over a channel. And so, yeah, that's anything, trees, linked lists, types that you define. And in Go, things are passed by value. So when you pass something over a channel, we're doing what you're talking about, where you're copying it effectively and then handing it off to something. The caveat there is that you can pass pointers, in which case you actually are sharing it, and that's your own fault. So in the original CSP specification, it's really a case of once you pass a value, you lose access to it, like we were talking about. So that's used for communication between processes, and you can pass data structures. And as far as the math is concerned, the values aren't shared. So there's a lot of different arrangements that you can have between processes and channels. And just to give a high-level overview, you can have the obvious one-to-one relationship. The boxes here would be processes, and then the fat arrows would be your channels. So in this case, this process is putting a value onto this channel that this process is able to pull off that channel. So you can think of it in a sense as sort of a publish-subscribe. And then you can have, obviously, extensions to this idea. You can put it on a channel that a lot of different processes are listening on. This, in this case, this is not really a publish system where each of these three processes is going to get whatever values you put on here. It's whoever grabs it off the channel first. So think of it as almost like a work queue. You've got these different workers who are all pulling items off, and when they pull one off, the others never see it. And so it's really a case of who got there first. Obviously, you have the reverse of this, where you've got a lot of different processes feeding data into a channel, and one other process consuming those, and then just the end-to-end version where you can have that. So that, you mentioned Erlang earlier. That sounds a lot about Erlang, except it's synchronous. So when this guy here puts a value on this channel, he sits there and waits for somebody to take that before continuing on. And obviously he has to wait if there's already a value on there. You can in Go and Core Async, you can get around that by making this a buffered channel and saying that you can put multiple, n values on it, and you won't block until you've got n values actually on that channel waiting to be taken off, and then you'll stop. But in this case, we're just talking about you put a value on, and you're just going to hang out until that value is taken, and then once it is, you can continue on. And the reason to do that is because then that gives you a point at which you can effectively synchronize between different processes, and it makes it a lot easier to reason about than, he just fired this off, and then where did that go, and then he went on to here. And so, but again, that's parameterizable. You can do a variety of different strategies. And so the other thing that's different from the actor model, such as in Erlang, is that you're putting values onto a channel. You're not putting it into some agent's mailbox. So this guy right here might not know anything about this other process. In fact, he doesn't, because processes don't really, they're not named at all. The only way that you can interact with them is via channels. So this guy is going to put a value on that channel, and he doesn't know whether that channel is listened to by anybody, by one process, two processes, five processes. He's just putting it out there at a particular place where other people can pick it off, where other processes can pick it off. Whereas in the actor model, you know about the particular instance of an actor, and that you're sending values to that directly. So we're going to get into Go now, and the connection between CSP and Go is fairly direct. Early on, Rob Pike worked on a language called Squeak, which was directly inspired by the CSP paper. And then he refined those ideas in a language called, creatively, NewSqueak. And if you look at NewSqueak and you're familiar with Go, you'll see a lot of the syntax in terms of the concurrency, the channels, and Go routines is shared with NewSqueak. So that's where it really started out. All right, so we mentioned processes and channels. What CSP calls a process, Go calls a Go routine, and they're being clever. In part, it's because when you're talking about computers, the term process is obviously overloaded. You don't want to create confusion with operating system processes and make people think that you're spawning a brand new process every time you create a new one of these things. And they also wanted to sort of invoke some similarities that it has with coroutines. Which are functions that you can suspend and re-enter and those sorts of things, because you can get some coroutine-like behavior with Go routines. And so, like I said, they're being clever. The other difference between Go and the CSP paper is the CSP paper really thought of channels as being one-way channels that you put a value on and they come out the other end and they never go back. In Go, you can create one-way channels. Most of the time what you see are two-way channels because it doesn't make a big difference. So a Go routine, the reason it says functions in here is because a Go routine in Go is really just a function that you invoke with the Go keyword. And that will create a new Go routine. So like I said, a note about them is they're not threads. So they're actually much, much more lightweight than threads. They're on the order of a few kilobytes. And so your program might have millions of Go routines, and that's not really gonna, you can still do that on a very resource constrained device. It's not something that would weigh you down like having millions of threads running at a particular time. So we're gonna go through some examples. One of the obvious examples is to do asynchronous IO. So how many of you have used JavaScript or Node where all you've got is asynchronous IO? So when you go out and want to get some data from disk if you're using Node, or you want to get it from an HTTP server if you're using it in the browser, you have to give it a callback. And when it gets the data back, it'll call that. Otherwise, it continues on with the execution. You don't have blocking IO. There are some special calls where you can get blocking IO, but generally speaking, JavaScript is going to be asynchronous. So Go by default is synchronous. So what we're going to do is we're going to switch over here and work out some examples. Let's see. All right. Okay. So just to give you a taste, we're gonna create a basic, I've got a couple servers running here which are slow so that we can see how it works to make HTTP calls. So I have those running locally there. And so we're gonna get the response. The underscore is because I don't care about the errors at this point. This is Vim. So we're just going to get, the B is bytes. We're going to get read all the bytes off of the body, and then convert those bytes to a string and print. So in order to do this, we actually need some imports.
Can you make your font a bit larger?
Yes.
Like a lot.
Yes, let me see what I can do here. Is that better?
Yes.
Okay, perfect. Okay. So this is a basic blocking call. And what we can do is we can just run that program. And we can see that it returns 2. And that happens to be how many seconds it waited before returning a response. So if we were to run this again, it's going to randomly choose some. It might be longer than 2 seconds because or 4 seconds because it's actually building. So to demonstrate that this is synchronous by default, we're just going to do this several times. And in Go, we have these weird little assignment operators, which also declare what type they are. And we just have to take those off since we're reusing those variables. So now what we're going to do is we're going to see this sequential happen sequentially. So we've got that one took 4 seconds, another one took 4 seconds, and then 2 seconds. And if what we do, let's just build this so we don't have to worry about that. And then if we time how long this takes, it should be fairly close to the sum of all the different numbers that we see come back. So, yep, sure enough, took about 6 seconds, a little bit longer. Can everyone see all right? I don't know if I'm in anybody's way. So that's a really basic example of the fact that Go by default has synchronous IO. And what we can do is we can go and we can make this asynchronous and say, you know what, there's no reason that we have to wait in serial, right? We can wait at the same time. So what we'll do is we'll create some Go routines, which, like I said, use the Go keyword, and then you're just going to have an anonymous function. And the difference is that you actually still have to have the parentheses on here to invoke it. But beyond that, this will create a new Go routine. So just wrap all these, and then, all right. So if we do that, then we can go run sync, and no output. The reason for that is because you've got a main Go routine, and then we fired up these 3 other Go routines, and then the main Go routine finished, and it said, we're all done. So what we've got to do here is actually tell it to wait for each of these to finish before exiting. And to do that, we're going to create a channel. So we don't have to create a fancy channel. We can just take one that takes a Boolean. And what we can do is once we've done this, we can say, you're done. And we need to do that for each of these. And this is not quite enough. We have to do one more thing, which would be to wait for each of those. So this syntax says put the value true on this channel, and this syntax with the arrow on the other side of the channel says wait here and return the value that you pull off this channel. In this case, we don't care about the fact that these are all true. Now, when we do this, we should see, hey, look, those two came at the same time. And and so if we time that, we should see that it only waits for the longest one. And so, yep, 4 seconds. So this is an example. You'll notice that in this case, these are all going to be in order because it's just the order or the time in which they came back. And this is an example of a really useless sorting algorithm called sleep sort. And generally speaking, is not very applicable to probably anything that you're doing. So this is an example where what we did is we took a language which by default has synchronous IO and made it asynchronous. If you're using JavaScript, you wouldn't have to do this. What you'd do is you'd pass functions and as callbacks, and we'll look at an example like that in a little bit. And they would pretty much do what this does right here, where they all go out and they just run down through, and then they all wait in parallel. So what we want to look at next is, okay, so that's an example of.
Now, just a minute, I'm just trying to
Sure.
make sure I understand. So done, you said is a channel.
Yep.
And you said channels don't buffer, they are synchronous, they take one at a time.
Right. So
What I'm seeing here is not 3 trues being buffered onto that channel done. It's just that it's waiting for 3 events coming off. I'm probably not using the right channel.
sure. So let's walk through this a little more clearly. So we're creating a channel, done, up here at the top. And then when each of these Go routines finishes and gets a response back, they're going to put a value on done. So what the main Go routine does is it creates that channel, fires off these Go routines, and then sits here on line 32 and just waits for somebody to finish. Right. It might be this 3rd Go routine, 2nd one, 1st one. It doesn't care. Once that one comes back, then it goes on to wait for the next one on the very next line. And then it goes on to wait for the 3rd one. And then once it gets back all these. This is a really terrible design in the sense that If I were to go in and add another IO call, then I'd have to go and add another done, and they're sort of separated in the code and be an easy thing to screw up. This is more demonstrating that it's very easy to take something that's synchronous and make it asynchronous in CSP, and which to me is a nice thing rather than having to choose a platform that either is synchronous or is asynchronous. You in Go have a choice. Whether you're going to have some event be a blocking event or a non-blocking event. Does anyone have any other questions about that? It's easy for me to go fast because obviously I know what's going on here. So if anything's not clear, let me know. Okay, so let's actually do the opposite of this and create a new one called async. Well, let's see. So we looked at asynchronous, taking something that was synchronous and making it asynchronous. Let's actually look at the reverse of that now, taking something that's asynchronous and making it synchronous. And this will, okay, so we're going to create a new file here. And what we're going to do is, let's say that we've got a function called fetch that takes a URL and a success function. And this would be very much like what you would see for IO in JavaScript, where you just give it a callback function. And that's kind of where you end up being stuck. So this is kind of a re-implementation of the JavaScript, say, AJAX call. But other than that, it's going to end up being just what we saw in the last example as far as the mechanics of making the HTTP request. And then we're just going to pass what we get back to our success function. This function doesn't return anything. The success function doesn't return anything. And that's some of the pain of dealing with purely non-blocking system, is that these values go into these functions and then it becomes a lot trickier to get them back out. And that's where things like promises are trying to help. So let's say that we're going to make a call to the same slow server, and we've got to give it a function which takes a string. And then what we do here is, let's say we just want to print that. And then let's do that a few times. And we'll probably have the same issue that we had before, where we have no output. So let's use a similar trick. We'll say and okay. All right, so I think those just happen to be in order. If we do this again, it probably won't be. Oh, right. What am I thinking? This is the asynchronous example. So the trouble is, say you wanted to combine all three of those bodies. You get back a response from here, here, and here, and if we wanted to add those up, we're not actually going to do that right here. But if you wanted to do that, you're kind of stuck, because you have this in this function, and you start having to jump through some hoops in order to be able to get values that get returned to those functions all in one place together. And so since this is how JavaScript works, JavaScript has some libraries for doing this, but they're not trivial. And so if you try implementing it yourself, you're going to run into trouble. So in this case, though, it's as simple as rather than waiting here at the end, let's just wait after each one. And then we should see that this takes as much time as it would if you were synchronous. So, okay, so it's not in order anymore. It's not synchronous, it's blocking. And so let's take a little bit longer look at what's going on here. What happens is when this one gets done, well, you run through on your main Go routine, this fires off a Go routine, this fetch function, and then it sits there and waits. And when this fetch function comes back and actually calls its callback, that's when this done channel gets a value, and here at line 24 we're able to continue on. And the same thing happens 3 times. So if we wanted all of those bodies in the same place, say we just wanted to print out a string of them concatenated together, that's as easy as changing this to a string and saying rather than printing, just send it back. And so now we should actually do something with this. Let's say we'll just make the result an empty string. And so then we can do something like this, and we'll just concatenate all of those, and then print the result at the end. This will actually, it'll look similar, but what you'll get is you'll get all your output at the all at once. There you go. So you, in this case, had to wait for 11 seconds in order to get that output, but you can see that it didn't all come together necessarily, but it did come in the order in which you did things in here. And you can play with different permutations of that in order to, maybe you don't care about the order, maybe you just want all those values at the same time, in which case you can go right back to what we had at the beginning where, we've got all of these happening at the same place, in which case they would all do their waiting in parallel, but you would still be able to get all the results out of these functions where they're effectively in sort of dead-end code, unless you want to go through some extra work. Does anybody have questions about that?
Show the fetch function one more time.
Sure.
I have a question, but it's not related to concurrency. I don't remember Go having a print function. I always used FMT. Has it always had print?
I couldn't tell you. I pretty much always used the format library as well and the print line and printf, and discovered that at some point that it had a print function. I don't know whether it's like not recommended for use, but so this is a good time to talk about something that Rob Pike, who's one of the inventors of Go, likes to touch on, which is the difference between parallelism and concurrency. Parallelism he describes as being a lot of things happening at once, or multiple things happening at once. So say you've got a web server and you've got lots of requests from different people coming in. You're handling them all in parallel. In order to be really parallel, you've got to have multiple cores. Concurrency, on the other hand, is what he describes as not doing a lot at once, but dealing with a lot at once. And the distinction that he draws there is that you can do, with concurrency, you can do concurrency with a single core, which means that you're not necessarily doing multiple things at once. What you're doing is you've got several different processes going, but in order for one to start, whatever one is running has to pause. And so think about it maybe like you're at work and you're working away on a problem, and then you get some email, you have to stop doing that and go deal with the email. And the email requires you to deal with getting a conference room or a calendar item, and you have to go and switch to another thing that you have to deal with. That would be concurrency. You're dealing with a lot at once. In a sense, you've paused your programming, you've paused your email in order to look at the calendar. You're not doing all 3 of those things in parallel. So that's some of the difference that he talks about between parallelism and concurrency. When in this example where we maybe wait all at once, it's deceptive because what you're really doing is it's more concurrency because you're dealing with each of these requests at the same time, but you're not doing anything with them. So you're not doing processing of an HTTP request where you're having to go to a database and do all sorts of processing while you're doing a bunch of other people's requests as well. This is maybe not the best example of that, but I think it's an interesting thing to consider when you look at, when you think about how to solve the problem. A lot of problems you don't have to solve in parallel, but it does help to think about them as being things that happen concurrently, different processes all at once that you might suspend and that work together, actually. So one of the other examples, uses for CSP is event coordination. So you might have a bunch of different processes doing stuff, and because they can talk to each other, you can actually coordinate between them much more conveniently than if you were trying to do it in, say, a system where you're working with different threads and they're having to pull some shared memory somewhere. We don't have to go into that right now, but if you're interested in that, let me know. And then the last example of what it's useful for is sharing. And I bring that up because Go actually has one of their mottos is don't communicate by sharing memory, share memory by communicating. So, and sort of unpacked what that means is that in a lot of cases, what's going on where you're using mutexes and locks and sharing memory and you've got different threads, what's going on is that you're really trying to communicate between threads, but the only way that you have to do that is by sharing memory between them. And then you're creating other problems. CSP gives you the option, it bakes in communicating between threads as your primitive, and then that allows you to share information between those processes over those channels rather than having to share memory in order to get information from one process to another. And it simplifies a lot, in part because you have some reliable rules for dealing with those channels, such as when to block and when you don't block. And so it's much easier to reason about, but it also makes the safer thing much easier to do. It deals with the polling really at the level of the execution runtime rather than something that you have to deal with. And so it's a higher level way of thinking about concurrency. So that's a fairly brief introduction to communicating sequential processes. I really like using it in Go. I have not done a really big application in Go, which would really take advantage of some of those things. I know that most of the time where I not encounter it, but where I wish I had it is working in other languages that don't have it. Anytime I want to do something in the background and you have to go and install some sort of job queue infrastructure in order to be able to just return a response while you continue doing something else. I always wish I had just a Go routine there that I could fling out and do. So the easiest way to get started, if you're interested, is to just play with Go or play with any of the other CSP libraries that different languages have available. I find that when I play with it, I understand it better, and when I understand it better, that actually enables me to use it.